Hi everyone, welcome to another video, and today we'll be discussing about a new question called find peak element. So the question suggests a peak element is an element that is strictly greater than its neighbors. Given a zero index integer array nums, find the peak element and return its index. If the array contains multiple peaks, return the index of any of the peaks. Okay, you may imagine that nums minus 1 equals to nums of n equal to minus infinity. So basically, it giving us hint that if if we are out of bound to left and out of bound to right, we can consider the value as minus infinity. In other words, the element always considered to be strictly greater than the neighbor that outside the array. Okay. So in that way, what happens if the last element of an array, means last index or first index, is a greater item, right? We can, because we are considering the leftmost and rightmost outer bound elements minus infinity. So the index 0 and index n in n minus 1 can also be peak. So then let's see what the question suggests on the whiteboard. Now then, take the example 2 that says the nums array equals to 1, 2, 1, 3, 5, 6, and 4. Okay, so what happened is it's saying that a peak is an index where the left and right elements are smaller than itself. For example, here, if you see, 2 is a peak because the left item of the of the of 2 is lesser than 2, right? And the right item to 2 is also lesser than 2, so it's gonna create a peak, right? Similarly, 6 could be a peak as well because it is greater than its neighbors, that is 4 and 5. So if we plot it in a graph, in a chart, it will also uh, produce a peak. So it says that find those and return the index, and any of those indexes is fine. And also it says that, for example, if we have a case like 5, 2, 1, right? Then 5 is definitely larger, so we're going to consider the outer bound thing as minus infinity. So 5 will become peak, right? Because it will be greater than minus infinity. Also, it is greater than 2. Similarly, to the right side also, if we find, for example, we have another element called 4, then 4 can also become a peak because we're going to consider the outer bound thing as minus infinity. Then 4 is larger than 1 and 4 is larger than minus infinity. So 4 can be considered as a peak as well. So that's the thing. So here there are some edge cases, like what if there is only one item, right? One item. Then definitely it will become peak itself because this will be minus infinity from left side, minus infinity from the right side, and this will be peak. And what if there is only two item? If there is two item, similar like whatever is larger, that will become the peak because we're going to consider it minus infinity and we're going to get it, right? And that's the thing. Now, as you see that this can be solved using binary search. So how are we going to solve it? Using binary search. Now let me show you that. Now create our I and j, right? Left and right. Remember that we have, if we create our LNR from the indexes, we're going to get a problem if there is only one item, because L and R will become this, and we cannot find mid, and we cannot find things to compare, right? So what we're going to do is we're going to always start L from -1, and we're going to start R from the length, not length -1, the index, but the length. Okay, that is n. Because in the question, this already it gave us a hint that the values are -infinity. So basically, this is -infinity. This is -infinity. So we're going to start our L from -1, and we're going to start our R from n. Now we're going to find our mid. Mid will become 3, right? Then what are you going to compare? When you get the mid, we'll see the neighbor of the mid is larger or smaller than the mid. So if the right neighbor is smaller than 3 or smaller than the mid value, okay, and the right item to the mid also smaller than mid, then our mid is the answer, right? We're going to return the mid. Otherwise, we're going to find which element is bigger than mid. We can transfer. If we find the bigger element to the right, we're going to transfer our L to there. Now we're going to calculate new mid. Similarly, if our larger element is to the right, then we're going to the left, we're going to move our right pointer to that left neighbor. So then what happens here? Now the new L will become mid, mid plus 1, right? And R will stay -infinity again, means n. So our new mid will become our 0, 1, 2, 3, 4. That is 4 plus 4, 5, 6, 7. 7. That is like 4, 4. 4 plus 7, that is 11 by 2, that is 5, right? So this will become mid. Again, we'll see this is now the mid value for right. Mid value is greater than the value to its right and the value to its left. So mid will be the answer. Then we're going to return the index, that is 5. The 5 will be the answer for this array. This is the basic concept. And if we start our indexes, right, from -1 to n, it will take care of the edge cases when there will be one element, because if there is one element, our mid will come here, then it will compare with -infinity and plus both the -infinity with the mid, and will return that 0 index. Now then, let's implement the solution using JavaScript. So the first thing first, we're gonna create our indexes, right? Create the I limit and j limit, or the R and left and right indexes. So let and right equals to, we're going to start from -1 to nums dot length. So 1 lesser than 0 and 1 larger than the last index. And the values of those indexes are -infinity. So now Uh, it's a simple thing now. While similar to all binary search, we have to write our, that while loop that will run on our left and right pointers. While let greater than equals to right, because we want our pointer to match. And then here, because we are considering the -1 and the length pointer, the out of bound indexes, we have to keep it, we have to write a check for that, because if mid goes out, or if mid goes to the left outside out of the bound, or to the right out of the bound, our logic will fail. So beforehand we have to check if our mid value is lies out of the bound. If it is, then we have to assign the value minus infinity to it. So let mid equals to mat dot floor dot left plus right divided by 2. This will give us our mid, and now then we're going to calculate our left and right values, so the neighbor values, right? So now let left value, or left neighbor, equals to, if like mid -1 greater than equals to 0, we're gonna return nums of mid -1. If not, we need to return negative infinity. So that will be like number dot negative infinity. Similarly, you're going to do for the right bound. That will be right neighbor, and you're going to do the same for mid +1, smaller than nums dot length, then we're going to return mid +1. If not, we need to return negative infinity. Now we are good. Now we are good with the values, and our mid will not going to go out of bound. Now we're going to write our comfort logic, like if our mid, like nums of mid is greater than left neighbor, and nums of mid is greater than right neighbor, then return what? Mid, because it asks to return us the index. So we're going to return that, return the mid. If not, else if if right neighbor is greater than nums of mid, then we have to move our left pointer to there, right? So our left will become mid. Let's not do mid +1, so that we can match the indexes, and because the value that mid can be a left neighbor, right? So we should not be doing mid plus 1 because we're going to exclude it. That's the logic, because if mid, in this case, if the mid is the value, the mid can be a peak, as means the mid can be a left or right neighbor. So let's not make plus 1 and minus 1 to the mid. Else right equals to mid. So this should solve our solution. This is a mid-level solution, but once you only thing that took me some time is to find out that uh, declaring the left and right pointer, or initiate the left and right pointer with the -1 to plus n, because otherwise it used to work. Only when you submit in the Leet code the error comes, then you find out, okay, the left and right pointer need to be declared this way, and it's solved. So that is the only tricky part I find here. Otherwise it's a straightforward binary search. By the way, first time I searched it using heap, because if you find the max element is a answer. So I find that long back I solved it using heap, but the question asked to solve it log n time. So that is like strictly a binary search. Anywho, now let's test it. Perfect. Now run it. And it failed. Oops, see, left and right. Anywhere else? Okay, left and right names are correct in other places. Now let's test it. Perfect. Now let's submit it to Leet code. And now copy. Perfect. Now run. Accepted. Submitted. So you see, this is one of the efficient solution. Again, so if you go to description, it says that strictly we have to find it using log n, that is like binary search, and this is the solution. So that's that. Thank you for watching, and see you on our next video.